going to be an example video for improper integrals, and we have this example right here. It says the integral from 0 to infinity of 2x over x squared plus 1. And the first thing I'm going to do before I try to solve this indefinite integral is to find the antiderivative, and then we're going to use that antiderivative to find the definite integral. So first thing you should notice is there anything we can simplify? In this case, there isn't. There's no simplification that we can do to make this problem look a little bit easier. And you should notice that there's no rules that we can use right away anyway until we rewrite this. And we're going to rewrite this using integration by substitution. And I'm going to use the most buried function, which is this x squared plus 1 as our u, which means our du would be equal to 2x dx, which is perfect because it's right up here. So then we have everything substituted for. From here, I'm going to just find the antiderivative really quick. So you're going to have 1 over u du, which means the antiderivative with respect to u is going to be equal to ln of u plus c. We don't really need the plus c though, but I'll just write it down for fun. Okay, the next thing I'm going to do is rewrite this improper integral a little bit better. Sometimes you're not really supposed to have this infinity as one of the limits of integration. So I'm going to put in the limit as b approaches infinity for the integral from 0. The problem with this though is instead of going to 0, because everything's in terms of u, I'm going to put this 0 in for x here. So I'm going to put it in here, 0 squared plus 1. So now our lower limit of integration is going to be 1 because we're in terms of u here. Okay, since b is approaching infinity, we want to put b up here. And if you notice right here, if you put infinity in for the u, you end up with infinity anyway, so everything still works out. And then we're doing 1 over u du. Okay, from here, we're going to have the limit as b approaches infinity of ln u, and we're integrating this from 1 to b. All right, from here we're going to simplify things. We're going to plug the b in to this ln u, so you're going to end up with ln of b minus, then we plug the 1 in, ln of 1. Okay, well, ln of 1 is 0, so we can just get rid of that. You plug in b, ln goes to infinity. So if you plugged in infinity here, ln of infinity is just infinity, and you end up with your answer. Now, if you notice here, the answer is infinity, so you would say that this limit diverges. This is kind of what I was talking about in the previous video. Because it doesn't have a value, it doesn't converge, you would just say that it diverges. But your answer is infinity for the answer for this improper integral. So real quick, I basically wanted to show you how this looks graphically and how it's not exactly intuitive to assume that the area ends up being infinity when you do an improper integral of this f of x function from 0 to infinity. So basically the integral was 0 to infinity of f of x dx. Now it's not going to actually register anything on this calculator. Let's see, limits of integration must be finite numbers. I'm just writing this in here to kind of show you. But essentially what you're doing is you're finding the area of this whole section right here. And if you zoom out, you'll notice that it's getting closer and closer to 0. That vertical asymptote is equal to 0. Now, how do we know that? Well, what you can do is you can take the f of x function and then just keep adding zeros in here to go to infinity, and you'll notice that it's getting infinitesimally closer to 0. Okay, as you can see, it's flatlining. Eventually, if I add enough in there, it's going to just round it to 0. So if this is going to 0, infinitesimally closer to 0, how does the area end up being infinity? Again, that's not really intuitive to understand. If you just looked at this just as it is, you'd say, oh, eventually it runs out of room because it just gets closer and closer to 0, so it's going to form that shape that you can find the area for. But that's not actually what happens here. Now, it happens sometimes. There will be certain examples when this actually does happen, but I just kind of wanted to show you that it doesn't happen here. One thing I could do is this indefinite integral in here, I can actually just start putting values in here and get closer and closer to infinity. So if I put 1 in here, 10, 100, you'll notice it just keeps going higher and higher and higher and higher and higher and higher. Whoops, until it runs out of room. Okay, now there are certain examples when this actually does work. If I just take this 2x and get rid of that right here, so instead of 2x, I put a 1 in there. Now, if I do the exact same thing, you'll notice that the horizontal asymptote is still 0, but what I'm going to do here is just add, or get closer and closer to infinity here, and you'll notice that the value actually starts leveling out a little bit. till it runs out of room. But it ends up with that 1.571, which is getting infinitesimally closer to. So a small change like getting rid of that 2x makes it so the limit all of a sudden exists and converges versus the other one that was diverging. I just kind of thought it would be cool to show that. We're going to talk about that more in class. So that's an example problem for improper integrals. If you have any questions about anything in this video, let me know.